Neutron star. A neutron star is an extremely dense celestial object that forms when a massive star undergoes a supernova explosion. During the supernova, the outer layers of the star are expelled into space, while the core collapses inward under the force of gravity. If the core's mass is between about 1.4 and 3 times the mass of the Sun, it will collapse into a neutron star. Neutron stars are incredibly compact, with a mass typically about 1.4 times that of the Sun but squeezed into a sphere with a diameter of only about 10 to 20 kilometers, 6 to 12 miles. This results in an incredibly high density, with a teaspoon of neutron star material weighing as much as a mountain on Earth. One of the defining features of neutron stars is their composition. The core of a neutron star is primarily made up of tightly packed neutrons, hence the name. Electrons and protons combine to form neutrons and neutrinos through a process called neutronization, which occurs under the extreme pressure and temperature conditions found in the core. This dense, neutron-rich matter is often referred to as neutronium. Neutron stars have extremely strong gravitational fields due to their high mass and small size. They also have rapid rotational speeds, and many neutron stars emit beams of electromagnetic radiation that can be observed as pulsating signals, leading to their classification as pulsars. Additionally, neutron stars can exhibit phenomena such as X-ray bursts, magnetar activity, and can even form binary systems with other stars, where material from a companion star is accreted onto the neutron star, generating X-ray emissions. Studying neutron stars provides valuable insights into the fundamental properties of matter under extreme conditions, gravity, and the behavior of matter in the presence of strong magnetic fields. They are also important in the study of gravitational waves and as potential sources of exotic phenomena, like quark matter and strange matter. How are neutron stars detected? Neutron stars can be detected through various observational techniques, and the detection methods depend on the specific characteristics of these celestial objects. Here are a few common methods used to detect neutron stars. Pulsar observations. Pulsars are a type of neutron star that emit beams of electromagnetic radiation that sweep across space as they rotate. These beams can be detected when they intersect with Earth. Astronomers use radio telescopes to observe the periodic signals, or pulses, emitted by pulsars. By analyzing the timing and characteristics of these pulses, scientists can identify the presence of a neutron star. X-ray observations. Neutron stars can also emit X-rays due to their incredibly strong gravitational fields and high temperatures. X-ray telescopes, such as the Chandra X-ray Observatory, are used to detect and study these emissions. X-ray telescopes are designed to focus and detect high-energy X-ray radiation, allowing scientists to identify the location and properties of neutron stars based on their X-ray emissions. Binary systems. Neutron stars can form binary systems with companion stars. In these systems, material from the companion star can be accreted onto the neutron star, resulting in the release of X-rays. By observing the X-ray emissions from these binary systems, astronomers can infer the presence of a neutron star. Gamma-ray bursts. Some neutron stars are associated with intense bursts of gamma-ray radiation known as gamma-ray bursts, GRBs. GRBs are among the most energetic events in the universe and can be detected by specialized satellites and observatories designed to observe gamma-ray radiation, such as the Fermi Gamma-Ray Space Telescope. The detection of gamma-ray bursts can indicate the presence of a neutron star. It's worth noting that these detection methods often work in conjunction with each other. For example, a pulsar may be initially discovered through radio observations, and then further studied using X-ray or gamma-ray observations to gather more information about its properties. How neutron stars die. Neutron stars can undergo several different processes leading to their eventual demise. Here are a few possibilities: cooling and radiative losses. Neutron stars are incredibly hot when they first form, with temperatures reaching millions of degrees. However, over time, they cool down through the emission of thermal radiation. The cooling process occurs through various mechanisms, including neutrino emissions, photon emissions, and the gradual conversion of the superfluid and superconducting components within the star. As the neutron star loses thermal energy, it gradually cools down and dims over billions of years. Spin down. Neutron stars are born with rapid rotational speeds due to the conservation of angular momentum during their formation. However, they gradually lose rotational energy over time. This spin down can occur through various mechanisms, such as the emission of electromagnetic radiation, pulsar wind, and the interaction of the neutron star's magnetic field with its surroundings. As a result, the neutron star's spin rate slows down, and it eventually becomes a non-pulsating, non-rotating object known as a unquat, dead unquat, or unquat, quiescent unquat, neutron star. Black hole formation. In some cases, a neutron star can accumulate mass through accretion from a companion star in a binary system. If the mass of the neutron star exceeds a certain critical limit, called the Tolman-Oppenheimer-Volkoff (TOV) limit, it will collapse under its own gravity. The collapse results in the formation of a black hole, a region of space where gravity is so strong that nothing, not even light, can escape. Supernova explosion. Although neutron stars themselves are formed from supernova explosions, there is a possibility of a second supernova event occurring. This can happen if the neutron star accretes sufficient mass from a companion star or undergoes a merger with another neutron star. The sudden influx of mass can trigger a new round of nuclear fusion and subsequent explosion, leading to a supernova. In this scenario, the neutron star is completely disrupted, and only remnants of the explosion, such as a nebula or a black hole, may remain. It's important to note that the exact details of a neutron star's death are still an active area of research, and there may be other mechanisms or scenarios that could lead to their demise. The study of neutron star evolution and their ultimate fate is an intriguing field of astrophysics. Enter your text here to convert text to speech now.